Welcome back, and we will close chapter 2 today. The last section we will be going over will be the SIR model of an epidemic. So this is a model which were used frequently for modeling an epidemic. For example, like COVID-19 can be the coronavirus epidemic we're going over with. It is a very typical application for the SIR model. So what is SIR model? For that, we actually, do everything based on a very simple assumption. We divide the whole population into S, which is the susceptible group. Which means the people who can be infected, the infected, which are the people who actually transformed from S to R. And finally, when they carried the virus for a while, they got cured, so they recover. Okay, and the interactions between them are this linear relationship. That is, a people who is susceptible is going to become infected once they're exposed to the virus, and the people who are infected will be able to recover after this. All right, now we need to set up differential equations. We probably need 3 differential equations, each one for each population. So the first one is S prime. The people who are susceptible should decrease because once they become infected, they will not be susceptible anymore. So this is going to be negative alpha S and I. Here, the more the population of susceptible, the more the infected people, the bigger the chance they are going to see each other and get exposed to the virus. And alpha actually quantifies those kind of infection rate. So that's the first one. Second one, the infected people will be the people who just got infected from S minus the people who actually got recovered. They recover by themselves. If they are opposed to susceptible, they become or recovered. That doesn't speed up how fast they recover. So that we don't have R here, like before. But before, if you put infected people around the susceptible people, that does speed things up. Okay. So finally, the R over dt. We are going to have beta I. It's just like all the people who came recovered from infected. We put these 3 together. We got the SIR model, based on very simple assumptions. Okay. Now, how do we solve it? Number 1, it's nonlinear, because we have a lot of multiplications together. So probably it's going to be difficult for us to solve it, but at least we can try to do qualitative analysis, which means equilibriums, phase portrait, and things like that. Second, well, technically we have 3 differential equations here, and everything we have done so far is on 2 variables, which means we have 1 more extra dimension. The good news is, actually, if you take a look at this, number 1, this one stands alone. It doesn't interact with other species that much. Second, if we just think about the percentage, we do have the S plus I plus R equals 100%. That means if we could model S and I, R we can get it from 1 minus S minus I. Then if we just focus on the first 2, you can see there's no R here. These 2 together forms a closed 2-dimensional differential equation system. With or without R, that doesn't change the dynamics of these 2 species. So what we can do is we can delete this. Okay, and only keep the first 2 because they do not involve R. This is something we call partially decoupled, remember? Then we can only focus on, we need only to focus on this. I dt equals alpha, here's S, Si minus beta I. So that will be the one we will be focused on. And moreover, we want to give them names. Alpha is almost something called infection rate. It tells you how fast people get infected. And beta is recovery rate. All right. We all know how to do phase portrait in phase plane. So let's try to do it. Of course, we use a computer to do the whole thing. Let's see. Let's just do face portrait. All right. So we take this SIR model. Moreover, we delete the last one. We only do the first two. And when we finish, we use the first two. Use 100% minus the first two. We got the third one. Okay. This will be the solutions we get from Euler's method, for example. Let's quickly see it. Oh, probably I can't do that. Okay. Yeah. At first, alpha is 0, which means no person get infected. The infection rate is 0. Therefore, you can see the susceptible, the infected, and recovered stay at 0. Okay. We start from 0.9 of susceptible. We have start from 0.1 for infected. They just stay where they are. They don't recover. They stay infected forever. And they don't get the alpha is equals 0, so people don't get infected either. Now what we're going to do is we're going to increase alpha. From here you can see, okay, very quickly all susceptible people drop to 0%. That means everybody become infected. So from here you can see, number one, it is exponential growth with the alpha. So it actually become, everybody get infected really quick. Okay, even quicker if you increase alpha. That is based on the fact that there's nobody recover from the pandemic. All right, now we are familiar with this. The next job is we try to increase beta a little bit. This time, you actually start to let people get infected, but meanwhile, the people get recovered. Now, from here, you can see, well, several things. Number one, people got infected. Eventually, they just hit a horizontal asymptote, which is equilibrium. After that, they don't get infected anymore. The reason is because they first get infected, and then the infected people got recovered. And as long as people get recovered, they do not get infected again. Okay, so eventually you will only have two types of populations: the people who are susceptible, the people who recovered, and the people who are infected. Eventually, they just all become recovered. Okay, so there's no room for infected. Up to here, you can see you stop at 60% because the other 40% has already recovered from the pandemic. Okay, there's no infected anymore. Now, try to think in your mind. If I just keep increasing alpha and keeping beta the same thing, what's going to happen? Number one, the infected people will increase. The faster the people recover, that got infected, the more infected people will have. But no matter how fast, eventually, think about it, eventually everybody got infected, then after that everybody recover. So eventually your infected will always drop to 0. It's just a matter of how long it takes. Okay, so if you just go back and see again, at first, if your alpha is small, your infected just drop like that. Okay, when your alpha become bigger, you can see you start to see a small increase at the beginning, a peak. Okay, the peak become even bigger. So this is what we will call an epidemic or a pandemic. Because if at first you have an infected group from your population, but they don't actually spread because they just keep having an exponential decay and eventually they just die out, we don't call this a pandemic because at first your infected people does not increase at all. We only will consider it a severe pandemic if you have this kind of small peaks. That means before the infection goes away, it will actually start to cause a lot of people to get infected. Okay, and from here you can see, even for small peak like this, people who got infected, people who are susceptible dropped like crazy. Okay, and eventually everybody need to actually recover from the infected. Okay, now if you increase beta, you can imagine what's going to happen. The infected is going to drop because they recover too quick. So it's almost like a computation between the infection and recovery. If your recovery is faster than the infection, there will never be a pandemic, right? Because everybody who got infected will automatically become recovered because recovery rate is faster than the infection rate. Then quickly this infection will be gone. But if your infection rate is bigger than the recovery rate, That's when you have people who constantly get recovered and they constantly get infected and they cannot recover in time. Therefore, you are going to see a peak in the infection. Okay, because you just don't have enough people recovering at the fastest enough speed. Then what's going to happen is they will stay infected for a long time until all people get infected. Then gradually, as time goes by, because eventually people recover, it will take you a long time to actually go from infected to recovered. And when you finish that, almost everybody has been infected before. Okay, it's not like the pandemic is going to stop anywhere. It's going to first infect everybody, and then finally everybody get better from recovery, not from not get infected at all. So there was a pandemic. And remember, this is the simplest model here. In real life, if you have some severe disease like COVID-19, you cannot just sit there and wait for people to recover, because during the infection period, people are actually dying. Okay, so what you want to do to prevent a pandemic is you really want to keep everything to be like no pandemic, which means the infection just drop like exponential like this. Okay, you never want anything that goes like a peak, because the longer you wait at the peak, it's kind of slow. Okay, you can see. The longer you wait at this peak period, the more people suffer, and if it's a fatal disease, they're going to die. Okay, during this period. So that's why we say we want to keep everything to be exponential decay from the beginning. We will show later how do we do this. Okay, how vaccine can help this. Okay, so that's the first one. Now the second one, we want to see the phase plane. Okay, same thing here. If you have no pandemic, let's see. Yeah, when everything is like that, you can see barely. You just stay at this is S, so susceptible stay at 100%. The pandemic just dies out really quickly. Okay, when you have a very slow infection rate. Now, if you increase the infection rate, okay, you keep increasing the infection rate, and go on, and go on. Okay, so what's going on here? Let's focus on several things. Okay. The first one I want you to focus on will be the susceptible people. That is on the horizontal axis. Oh, this is really slow. Okay, let's wait a little bit. All right. So the first one I want you to focus on is the susceptible people. Okay, at here, you basically start from 100% and you probably drop to 90%, and then the pandemic stops. So there will be 90% people who didn't end up being infected, and 10% end up getting infected but eventually recovered. That's nice. Okay, now we increase this. Horizontally, can you see that? This time, you went from 100% almost to 0.1, which is 10%. That means 90% of the people end up getting infected and eventually recovered. And only 10% people who actually end up not being susceptible all the way, they never got infected. Okay, so as you increase the infection rate, more and more people get infected. Fewer and fewer people stay susceptible all the time, which means that they were never infected. If you increase that thing to extreme, okay, you can see everybody got infected. Okay, they just eventually recovered. Okay, so everybody suffered through the pandemic. That's one thing we want to focus on. All right. The second thing I want you to focus on is actually the infected people. Particularly pay attention to the peak. The peak will be where the most people are infected due to the fast spreading of the disease, and they will stay there for a while before they actually recover from that pandemic. So at first, it's almost zero. You can see the peak. Now, if you increase this, you can see the peak is almost like 0.3%, 0.3, which is 30%. So during that period, actually at the peak level, you have 30% people who got infected, who eventually recovered. Now, increase that. This time you got 50% of people. Okay, and if you keep increasing the spread of the disease, or if you actually lower the recovery rate of the disease, you can see at a peak level, you will have more and more people stay infected. They will eventually recover if you wait long enough. But what if people are dying from the disease? Then there's no way for you to wait for them to recover. Okay, so that what we will call a pandemic occurred. All right, so let's write down the phase portrait. Actually, let's do the rough graph first. That is what we had before. So first one is numerical method. Okay. Okay. Depending on initial condition, but roughly, what will happen is a susceptible drop. This is your S. Okay. The infected goes like that. Eventually, of course, I didn't draw it carefully, but eventually they will go to 0. So this will be the infected. This will be the recovered. The period here we will call a pandemic. Okay. To make that happen, what you need is a big alpha or a small beta, which means fast infection, slow recovery. Okay, so the whole game is actually playing with these two numbers and try to make sure that which one is faster. If the recovery is faster, what you're going to get is something totally different. That would be the susceptible, just stay like that. So eventually there are a lot of people who didn't even get infected. They don't even need to recover. The people who originally got infected will recover, but only a few people. And then the infected people will be like that. In this case, there's no pandemic. Roughly, it corresponded to a slow spread and a fast recovery. And from here, you can see it's actually relative, right? So what you need is probably some number like the ratio between alpha and beta, or beta over alpha, whichever way you want to do it. Okay, so that's what we had from the graph. Now let's look at the face portrait. Okay, roughly what you're going to have is something like this. S and I, we cannot do R because we only know how to do 2 dimension. A little bit like that. Okay, so this is where the pandemic happened because that's where the peak of the infected. Okay, and we also know at here, basically the direction field is going to give you something 0. Before that, it was going up. After that, it was going down. Okay, so later we can see by this feature, we can somehow calculate where this peak is. That's roughly what we have for the face portrait. And for this one, your infected is going to just drop. So you start from here. Okay, your susceptible is going to drop. Your infected are also going to drop really quickly. So roughly you stay at here. In this way, we have no pandemic again. And from here, it's basically that the peak is actually here. But when you start, you already started over the peak. So you only take the drop part. So next time you see this, I think it's useful to think about an increase case where you're trying to hit the peak, and then the decrease case where the pandemic has passed. Now we're just at the end of the infection. We're just waiting for people to recover. No more people will get infected. Okay. So for the no time pandemic case, it's basically like you started here already. So there's no peak part from the beginning. You just drop. All right. So that's roughly the qualitative analysis of what's going on with SIR. Now, what are some interesting things? Well, the first interesting thing is I roughly want to know the shape of this thing. Okay, what this graph looks like. Is it a half circle? Is it a parabola? Because once I know the form, I will know, okay, where the derivatives, where things are going to go really fast or slow. That's one thing we want to talk about. So that's the face portrait. Worth mentioning. Okay. The second thing we want to talk about is, number one, where this is. Where is this number? Okay, where is the peak? And second, what determines do we have a pandemic or not? Okay. Can we know ahead of time, are we going to have a pandemic or not? Okay. And then after that, we will know how to control, how to do something in order to prevent the pandemic. So that will be the two jobs we want to do now. Let's focus on the first one. Can we somehow get an estimation of what this one looks like? What this curve look? Okay, remember, if we could solve it, we will, but we cannot. So what we can do is, we can do an approximation. ds over dt, okay, equals negative alpha si di over dt equals, this is what we got. All right. So now what I will do is I will take these two equations. I take 2 and divide it by 1. That's the left divided by left. So t is gone. The good news is every single term has an I. So the first one actually got cancelled. Let me write it out for you to see. The first one is negative 1. The second one is going to be plus beta over alpha s, or more precisely, beta over alpha, which is a number, times 1 over s. Okay. So what do we have here? We have a function, okay, which involves, we have a derivative, which involves I and s, not time anymore. So this is the changing rate of I with respect to susceptible population s. The right-hand side is nothing but a function of s. So this is almost like di over dt equals negative 1 plus a constant times 1 over t. You can simply just take the integration to get what I is. Not in terms of t, but in terms of s. So if you integrate both sides, I will put this one first. Or actually, let's put that one first. Then the left-hand side gives you nothing but I, okay, as a function of s, of course. And that's what we need, right? We're doing things in IS plane. This one gives you negative 1, so negative s, plus beta over alpha ln s. We should use absolute value, but we are assuming that s is positive, which is reasonable, plus a constant. Okay, that basically means, okay, the curve we have here, which is in IS plane, which is I as a function of s, is going to have the shape like that, if we take s to be the variable. Fantastic. Now what do you need? You need to figure out c. For that, you need an initial condition. That's why I say this is an approximation. Everything up to here is correct. But in order to get that one, we make an assumption. We'll assume that S0 is almost 1. That means when we start with, we only have a very few part of the population get infected. Maybe it's almost like 0.99. Instead of we start with 0.2, and we already have 0.8 infected. Okay, so let's say we already start early. We detected the infection really early, so up to now we only have a few infection, and the vast majority of the people are susceptible. So that's the assumption. Based on that, you can plug in. So I S0, that means I1. So let's see, at T0. Almost equals 0 then. Okay, at t0, I1 equals -1 plus beta over alpha ln1 plus c is going to be 0 because I1 let's try to make sure it's clear. It equals 1 equals 0. This is s equal to 1. Okay, so in case you become confused, here I mean I as a function of t, but here I mean I as a function of s. So this is 0. You have c equals 1. So finally, this is the curve, which is what we draw in the phase plane. All right. That only works approximately because we assume that we have to have this condition, that is s at 0 is almost like 1. Okay. With that condition, we will have an approximation, a very nice approximation of this curve. Good. The next job is try to figure out where this is. You know, what is this critical peak of my infected? That is very easy to do. You're basically looking for the maximum of this one. You just take the derivative with respect to s plus 0 and set it to be 0 because that's exactly where the whole thing becomes horizontal, right? So with that in mind, what you can do is you can simply solve it. Beta over alpha times 1 over s is 1. S equals beta over alpha. So this is where it happens. It's beta over alpha. All right, that's what we get. And we will give this one a name. Beta over alpha. We will call it 1 over r naught. Okay, because we want our r naught number to be defined as alpha over beta. So here, you can write it as beta over alpha. You can also write it as beta 1 over r naught. Later, we will actually discuss this right away. What does this r naught mean? All right, so that's the ratio. Cool. So number 3, the r naught number. We're talking about, you know, how to prevent a pandemic. Okay, and for that, what we want to do is we want to look at the difference between these two curves. Okay, ds over dt equals negative alpha I, di over dt equals alpha I minus si minus beta I. Pandemic or not pandemic totally depends on the infected. That means we need to ignore this and focus on this. Okay, so what can we do? We can do di over dt, which equals alpha si minus beta I, but what we can do is we can take I out. Okay, we can also take beta I out. Then what we have is nothing but alpha over beta s minus a 1. Okay. So which case do we have? The pandemic or not pandemic? Really depends on initially is this one positive or negative. Because if this one is positive, so these two are always positive, right? So if this one is positive, that will imply the derivative is positive. That will imply your infected will first go up. Eventually it goes down, but first it will go up. Okay. If initially this is less than 0, that means from the beginning, di over dt is less than 0. Therefore, from the beginning, this one should go down. And after that, you will go even more down. Okay. So pandemic or not pandemic really depends on what happens here. More precisely, what will happen. Okay, to the derivative of the infected. So if we write it down, we start to see a critical number. That is alpha beta s minus 1 equals 0. This implies s at 0 equals beta over alpha. And again, like we said, we call this one R naught. Okay, now we can say pandemic requires R naught bigger than 1 over S0. Or more precisely, actually, I prefer to write things in this way. S0 is bigger than 1 over R naught. Non-pandemic, which means S0 is less than 1 R naught. Okay. Here, R naught is a ratio which quantifies the infection and the recovery together. Big R naught means relatively fast infection and relatively slow recovery, so bad. Small R naught, good or safe. Okay, so that's the whole thing we have here. All that matters is 3 things. Okay, the first one is how fast is the infection rate. Second one is how fast is the recovery rate. The third thing is actually what's your initial susceptible population. Okay, if you have a really fast infection and if you have a really slow recovery, which means bad, but if originally your susceptible people are really small, then we don't care too much about it because you will still just drop because you don't have anybody left to be infected. Okay, so either way, we need to play with these 3 numbers. In fact, only 2 numbers because we only care about the ratio between alpha and the beta, and that will determine do we have a pandemic or not. Okay, judging by the graph, this is also easy to see. We just did the graph. We just know this is where the pandemic happened, which is 1 over R naught. So if S0 is bigger than 1 over R naught, remember S is actually the horizontal. Okay, axis bigger means it's to the right of this, then you will still experience a increasing, which is a pandemic. But if from the beginning your S0 is here, which is to the left of your 1 over R naught, you will only experience a drop. You will never go back because the whole trajectory goes that way. Okay, goes counterclockwise. So do you have a pandemic or not really depends on which location on this curve you are right now, or when you begin. Okay, to the right you will still go up until you hit the peak, and then eventually you go down. If you're already going down, everybody's dropping, then that's fine. All right. So what does vaccine do? Okay. Vaccine will actually take your S0, okay, and it will make S0 drop. Because as long as you got injected with the vaccine, you will not be susceptible anymore, right? So it's very possible that you have S0, which is bigger than 1 over R naught, which is going to have a pandemic. Now my job is try to, go down and give you a vaccine such that S0 drop to a level that S0 become less than 1 over R naught, and there's no pandemic. So that's what vaccine is doing. It's not going to change your alpha and the beta. It's not going to change how fast people recover or how fast people get infected, but it's going to change S0, which is how many people are susceptible from the beginning. Okay, so in real life, what do you do if you just want to use this simple model? What you want to do is actually when you have a disease or pandemic breakout, you want to first estimate R naught. Use your data. You want to actually use your data to see how fast things are spreading, and how fast people are recovering, or even people are recovering at all. Estimate R naught first. Once you have R naught, what you want to do is you want to use R naught to determine, once I have the vaccine, how much population should I inject the vaccine to? Okay, for example, you estimate your R naught is going to be 0.2, which is not too severe. Okay, you have how to see, no, probably not this one. R naught equals to 2. Okay, then what you get? You got 1 over R naught is going to be 1/2. Okay, so it's a relatively fast spreading compared to the recovery rate. Then what you can do is just inject the vaccine and make sure 50% of people, bigger than 50% of people actually, gets vaccine. So if you inject 60% of the people, you don't have to do anything after that. The pandemic will just generally go away, assuming that you estimate the R naught to be correct. If you have R naught to be 5, which is faster than this, then what you're going to get is 1 over R naught is going to be 0.8. Okay. That means you need to inject more than 80% of the people to make sure that the susceptible is below 0.8 gets the vaccine. So the bigger the R naught, the more people has to be injected. Okay. For example, if you have beta equal to 0, which means nobody recover, your R naught is infinity. Okay. Then 1 over R naught is going to be 0. Okay. This means everybody gets vaccine. There's no way, because people don't recover. So you can actually use this one to estimate how much effort you need to put into the, the spread of the vaccine. And also, if you have R naught equals to 0.2, 1 over R naught is going to be 1 over 0.2 is 5. You just want your initial value is to be less than 500%, which no matter what you do is going to be less than 500%. From here, you can say, well, there's nothing you can do. Actually, there's nothing you need to do. No vaccine is needed. This one will die out no matter what. So initial estimation of this R naught number is going to be super important. Of course, there are some other strategies you can take in order to prevent from the pandemic, because you can also change R naught. Vaccine change as 0, right? So how do you change R naught? Stop the pandemic. Okay, the first thing I just want to right here, use vaccine, such that S0 is going to drop. That will help preventing the pandemic. The second one is you can actually drop alpha. Okay. Slow down the spreading. That's where we do the quarantine. Okay, maybe you need to wear a mask. Maybe you need to stay away from crowd. Okay, sounds familiar, especially during the COVID-19 period, right? You can also increase beta. You want people to recover faster, so that's better medical care. Okay, or just make people to exercise so they stay stronger, their immune system become stronger, and things like that. So from here you can see there are all kinds of strategies you can take, but they change different values. The key is still look at R naught, and the key is still look at vaccine. You can even think about if every single one of them actually take resources, which one is going to be the cheapest one, the most efficient one, to achieve the same kind of phenomena you want. So that's very, very useful already. You will see in your writing project a chance to actually, do the COVID-19 model by yourself using simple SLR model. All right. So everything we have with SLR has been done. I think most of them are qualitative, except for you use numerical method to find the phase portrait. But I think we understand this thing pretty well. Especially the most important thing in practice is the definition of R naught number and how that thing actually affects. Do you have a pandemic or not? And also how that thing affects, like even if you have a pandemic, how soon will that thing go away? That's why when we have COVID-19, it's crazy because alpha is super big. The virus spread is super fast. Okay, and it's also difficult to recover. So once let's say alpha is big enough, and beta is basically what you have in the emergency room in the medical care resource, and nothing has a cap. So once your beta stop improving because all the ER places are occupied, and your alpha keeps increasing or stay high, that's when people, when we say like the medical system is going to crash and the whole thing become a disaster, which is roughly what happened back then. We were trying to prevent that, and that's why we have saying like everybody stay grounded at home. We have the lockdown in order to keep the R naught small. All right. So number 4. Oh, by the way, if you think about it, it's pretty scary because you saw the curve, right? The people who are susceptible actually got infected really quick for even very small alpha, because this is actually exponential growth. Okay, this is more than exponential growth, because as the infected people gets bigger, not only you have alpha with yourself, you also have I here. Okay, so if both population goes up, it's going to be even faster. That's why at first we thought like, a few hundred of cases, we didn't take too much care of it. And then after that, within 1 month, probably we have several 100,000. And for now, we have probably 2 million, maybe 20 million. I don't follow it anymore. But yeah, you can see that. So number 4, we have the modified SIR. I think you are already seeing this. The model sucks. Like, it's great. It's a very simple idea, but it definitely can be improved, right? So I will just introduce several models that you can think about. I won't talk about the details. The first one is SIR modified to consider vital, and basically it means birth and death. So before, what we were saying is ds over dt is going to be negative alpha I, assuming that there is no new supply of susceptible people. But we could add something that is going to be new S, which means we still have a natural exponential growth for people giving birth to newborns, and the newborns are actually susceptible. So that's something we can add for newborn. Okay. Something we can also add, di over dt. We can have alpha si. I keep forgetting this. Okay, but then we minus people who recovered. We can also minus people who are dead. Fatal rate. This is more suitable for pandemic COVID-19 because people actually can die from that virus. So eventually they never wait until they recover. We can also have SIR model, and we have the loss of immunity. Okay. Before, we have dr over dt equals beta I. That's the people who recovered. But after that, we stop there. But now what you can do is actually you can minus another new r. Those are the people who actually become reinfected, or just like say people who become susceptible again. That means if you actually build a immunity towards a certain kind of virus, but then you either lose it or the virus actually has the mutation. Once the virus have a mutation, you have to actually come back and become susceptible again. Therefore, your ds over dt is going to have the old thing. But this time, one more thing, that is, how fast people become reinfected again. So this is almost like to measure the infection. How to say? People who become susceptible again. So this can be due to loss of immunity. Or equivalently, it can be due to the mutation of the virus. That is actually a model more suitable for flu. Every year you take a flu shot. Flu shot is nothing but a vaccine to keep the people who are susceptible to be below a certain kind of percentage, so that we don't have a pandemic. But why do we do it every single year? Because the virus, the immune system that works for last year's virus does not work for this year's virus, simply because there is a mutation. Okay. Flu shot. So let's just put it here. Number 3, we can have the SER model. So we add one more phase to the whole thing. Here E stands for exposed. We can have some people to be exposed to the virus for a considerable amount of time without being identified as infected. So see, if you think about COVID-19, we have people who has no symptoms for 2 weeks, roughly. Okay, those people actually carries the virus, but they do not show any symptoms, so we cannot identify them as infected. In this way, we actually have a SER model with 4 stages. Which is more realistic, especially for COVID-19. Okay. Then what you can do is you can actually ds over dt is going to be negative alpha si. Fine. Not si anymore. Se, because they got exposed. dE over dt is going to be the people who just got exposed minus the people who actually get infected. Minus the people who, let's just say, I don't want to use beta. Note there is no I here, because once they are already exposed, they do not have to be close to the infected people in order to be become infected. Okay? It's just purely due to them. They already carry the virus. And then everything else carries. And finally, dr over dt is recovered. Okay, so that's some variations of SIR, and from here you can see you can add all kinds of things in. For example, you can have the loss of immunity combined with SEIR, or you can have the loss of immunity plus the vital information plus SEIR. You can have all those kind of things to make the model more realistic, depending on which kind of disease you have. Okay, that will be very, very interesting. All right, that's the variations. And finally, some other things for you to think about. SIR model, or SIR-based model with all the variations, is some model we use to model pandemic or the spread of disease. Now, can you use it for anything else other than pandemic? That's when you think about, what kind of things are very similar to pandemics. It's like when people get susceptible people get connected with infected people, okay? Then you can easily see, okay, if you have a network of computer, okay, each one corresponding a server to a server or a machine, and they're connected in all kinds of way. Okay? Or you can think about these things are Twitter accounts who follows each other. Okay? One directional or bidirectional. Either way, what you have here is you can have the spread of not a virus, but you can have a spread of computer virus. You can have a spread of informations from the internet. So you get like one people get to post of Twitter, and other people just retweet it. It's almost like getting infected, and eventually people forget about it. So then it's like recovered. So using SIR model, it has wide applications in the spread of information and many other things, of course. So if you're interested, check Google and try to see the spread of information, okay, and try to see how people use SIR model for that, okay. And then it's no surprise that you will see people call this epidemic spread of information. You will see this kind of metaphor a lot. Now you see, well, it's actually not coming from nowhere. It is rooted on the spread of the virus model, which is SIR. All right, that will be everything we need for chapter 2. In chapter 3, we move on to another view of solving system of differential equations using matrix.